This is today's content to present. I will review last week's main content and finish the explanation about superstructure and high-strength concrete which is used for this building. Last time we discussed about the core system of building. There were several options of deciding which structure system would be proper in economical and workable aspect. The concrete core and concrete tube with steel frame slab was selected due to the stability and economic efficiency. The structure consists of 16 concrete columns and cast-in-place reinforced concrete core, which was proper in enduring wind load. This system solved the difficulties of the 450 meters skyscraper by taking advantage of the steel and concrete. The overall structure shape was constructed in a tube-in-tube manner. Tube-in-tube method refers to the form in which a coupled structure system by soft outer tube around the exterior and a stiff inner core. By using the stiffness difference of outer and inner tube, they resist lateral loads such as the earthquake and wind. In between the outer tube and the inner tube, concrete beams are also used to connect them, and steel frame is placed on a concrete beam. It is mainly used because of its economical efficiency and, more importantly, the quick constructing process. Also, it could bear very high vertical load capacity up to 150 kN per bracket with wider platform and higher loading weight. The outside of the core uses a jump foam, which is advantageous for use from lower layers than the self-climbing foam. Moreover, it is convenient for adding connections and extrusions at the floor level due to the discrete features. And next, basic concept of outrigger. First, core and perimeter columns are located in building. An outrigger is connected between core and perimeter columns as a structural member. This type of connection improves the lateral resistance and strength of a high-rise building. Let's see the detail. Concrete core wall is basically placed in center of the building, and mega column and perimeter column surround this core, and steel belt truss supports laterally these columns, and 4 outriggers are connected diagonally to the mega column at edge. So lateral load caused by high wind drift and moment is mainly transferred through outrigger, and this outrigger is installed when building at 38 and 39 floor. The overturning moment is reduced about 40% by outrigger. If without outrigger, this 450 meter building will bend laterally. And also we can check bending moment and lateral load of the building. Bending moment is mainly concentrated on center and placed near this location. Outrigger resists this concentrated moment. Lateral load occurs near the top of the building, and outrigger holds this upper load and bending of the building. Next is frame of the building. The shape of outer frame constitutes star of an octagonal plan, representing the unity, harmony, stability, and culture. However, the exterior walls were so close to the core of the building, and it became undesirable designs for space use. Therefore, the shape of this octagonal star was designed with a circular shape inserted into the inner vertex. These 60 vertices were fit with columns, and a ring beam was installed to connect each column. And the frame of the vessel was designed in the form of a similar shape of a main column. And these 16 columns are charged with high-strength concrete, which is called CFT column. Such a system is a type of outrigger beam that connects the outrigger and the outer frame on the 38 and 39 floor. The CFT column is more effective in confinement and compression than the steel column, and also has excellent bending stiffness, which is necessary condition for high-rise building. Not only concrete, steel was also used for these long-span floor beams and support concrete-built slabs. And each of the curved or pointed steel plane is cantilevering beyond the perimeter columns and determine the entire external shape of the building. Another characteristic part of the Petronas Twin Tower is the bustle part. Bustle is a small circular and 44-story soft building attached to the side of the main tower. The bustle part not only brings about a change in the shape of the Twin Tower, but also has the effect of securing space, which is decreased by massive core. The bustle part is a reduced circular shape of the main tower, with 12 columns in charge of the structure. Due to the weight decreasing with height of the building, the column of bustle tower supports less weight than main column, so its diameter is also smaller than main tower. Next is exterior material. This building is located in the tropical zone near the equator, so the sun shines in all directions of the building, and also it rains a lot. The material of curtain wall of the building is designed to cope with these conditions. Because of heavy rain and many radiation, it used stainless steel for preventing corrosion and laminated green glass for preventing penetration of radiation heat. And also 33,000 panels are used for curtain wall. This stainless steel has various chemical elements against corrosion, and responding with oxygen and water, it forms very thin and stable film on metal surface and prevent corrosion. Also, the building is shaded through the sun shading attached above the glass of the module. It not only creates depth on facade and also improve energy efficiency. We have talked about core system and superstructure of Petronas Twin Tower in construction order, and now I will explain about the materials high-strength concrete used in this building. The strength of normal concrete used in general buildings is usually 30 megapascal and can bear loads up to 25 tons. The strength of the concrete used in Petronas Twin Tower is about 50 to 60 megapascal. This high-strength concrete can bear loads of up to 60 tons, and additionally about 80 megapascal concrete was used for the lower part of the building. High-strength concrete was used in the central core, perimeter columns, perimeter ring beams, and outrigger beams. As you can see in this picture, one feature of a high-rise building is its weight reducing with height. So, with the consideration about this feature and also expensive cost for high-strength concrete grade, it was determined that concrete grade reduction should be made first, and then reduction in wall thickness, even though this results in greater total concrete volume. High-strength concrete option was selected due to some benefits. First, it has structural efficiency. Columns of high-strength concrete carry vertical load at a cheaper cost per unit load than that of steel. It not only gives the efficiency of cost, but also the advantage of reductions in member size at lower levels, therefore saving more space. Last, by using concrete instead of steel, the average density got higher, leading to improving comfort under windy conditions. Also, the concrete core, columns, and ring beams contribute to the damping values and providing occupant comfort without the cost and space penalty of special damping service.